Okay, we're going to work an example problem with network of resistors and finding the equivalent resistance of the network, and then using the equivalent circuit to determine all of the different currents and voltage differences in the original circuit. And so this is a problem from the Walker textbook, Chapter 21, Problem 49. I've got a circuit diagram that the problem gave, and I've got a list of known resistances and the voltage difference of the battery. So the first thing we want to do in any circuit problem is make a good circuit diagram. This is a good start, but we're not finished. We need to label a number of other things. So this is called delta V bat, providing that voltage difference. We need to label all of the different conventional currents with an arrow on the wire. So this wire comes out of the battery, so that current is called I bat. We have a junction here. I'm going to go ahead and label that junction A. We're going to use that junction at some point in our solution. At that junction, the current I bat is going to split. So we have a wire coming out that way that goes through resistor 2, so I better call that I2 to match R2. And then this wire passes through resistors 3 and 4, which are wired in series. So the current there, I'm just going to call I34. That is the same current passing through I3 and through resistor 3 and resistor 4. Then we have another junction down here. I'll go ahead and label that junction B. And at that junction, I34 combines with I2 to make the current that passes through resistor 1, but I'll go ahead and label that I1, but I can see that I1 is also equal to I bat because resistor 1 is in a series with the battery, so these currents are equal at all points. Alright, so I've labeled my currents, I've labeled every little element of my circuit. The next thing we're going to do is make an equivalent circuit. So, and at the end of the problem, I'm going to fill in a table that's going to have the current, the voltage difference, and the power for every little element of the circuit, the battery and each of the 4 resistors. So that's, I'm going to fill that in as I go. Okay, so like I said, we're going to take this network of resistors and convert it into an equivalent resistance to make an equivalent circuit that only has one loop, and that's going to help us with our analysis. So the first thing we're going to notice is that these 2 resistors are in a series, and so we're going to make those into an equivalent resistor that I'm going to call R34. Alright, so I'm going to show that step here. So I've got R3 and R4 is equivalent to a single giant resistor, REQ34. And I can use my equivalent resistor in a series formula for resistors 3 and 4. I just add together resistance 3 and resistance 4 to get that total. And so that's going to be 6.2 ohms plus 12 ohms. So that gives me 18.2 ohms. So that's known. And so my original circuit, which was this, I'm now going to replace by kind of an intermediate step equivalent circuit with these 2 guys combined. So now my original circuit, which I'm not going to redraw, is going to be equivalent to delta V bat this is R2 This is my R equivalent of 3 and 4, and I still have R1 also down here. Okay, I'm not going to redraw the currents this time because I'm just trying to combine the resistances to find an equivalent circuit. So the next step I can show, I can notice that this equivalent resistor 3,4 is in parallel with R2. I know that they're in parallel because they're connected by a wire at this end, and they're connected by a different wire at this end. So that means the voltage at this end are equal of these two resistors, and this voltage is equal at this end. Therefore, the voltage difference is equal, and that's what we mean by parallel wiring. So that's an important thing to remember. Parallel wiring means same delta V. Well, that's how I can identify parallel wiring. All right. Therefore, I can make a new equivalent resistor out of these two. So I'm going to call that equivalent resistor 234. All right. So I'm going to use my REQ in parallel formula this time for resistors 2, 3, and 4. So when I have two or more resistors in parallel, what I need to do to find the equivalent resistance is take the reciprocals of each of the individual resistors and then take the reciprocal of my result to get the final equivalent resistance. So that will be 1 over 7.5 ohms, which is R2, plus 1 over 18.2 ohms, which is the result I found up here for R equivalent 3,4. I have to take the reciprocal of the final result. Alright, that turns out to be 5.31 ohms. So that's R equivalent of 234. Alright. That's taking these two guys to make an equivalent resistor. So my final equivalent circuit is going to have battery, R1, and then an equivalent resistor for these two. So I'm going to draw it one final time. Delta V bat. I'm going to draw a big REQ of 2, 3, and 4, and then I still have R1 all by itself. So that's equivalent to the circuit I started with. Alright, I could combine these two, but I'm not going to, because this, I've got it down to a circuit now that has one loop, and that was my goal. So on this circuit, I'm going to label, there's only one current, which is I bat, coming out of the battery, and that same current passes through both of these resistors and then makes a loop. I'm going to draw my loop going around the circuit in the same direction as that conventional current, ending where it starts at the negative end of the battery. And then what you want to do on once you have your equivalent circuit with a single loop, you want to write the loop rule for this equivalent circuit. So we want to add the voltage differences and sum them to 0 around that loop. Okay, so I get plus delta V bat. It's a plus sign because the voltage is rising in that direction that I've drawn my loop. The voltage doesn't change in any of these wires, but the voltage drops when I go through any resistor. I'm going to put a minus because it's a drop. That's the delta V of 2, 3, 4. And I'm going to put absolute value because what we're dropping by an amount, a magnitude, which is going to be a positive amount. But because it's a drop, I'm putting a minus sign, so that all of the changes can then add up to 0. Okay. Now I've gone through this resistor. Now I still have this wire. The voltage doesn't change. I have one more voltage drop. I'm putting a minus because it's a drop for delta V of resistor 1. This is representing the magnitude of that drop. And those together have to all sum to 0, because now I'm back at the beginning of the loop. Okay. So now I'm going to apply Ohm's law for each resistor. We can use Ohm's law for equivalent resistors, just like we can for real resistors. We're not going to use Ohm's law for a battery, because Ohm's law doesn't work for batteries. So delta V bat is just delta V bat. But for a resistor, I know that delta V is IR. And so for this resistor, the current is I bat, and the resistance is R234. And then for R1, I got a minus sign from the drop. I get I bat, which is the current through R1, times R1. And then that equals 0. And so I'm going to put a box around that, because that's kind of an important result. That's the way to write the loop rule for this circuit, with Ohm's law subbed in. Alright, doing that, the only unknown I've got is I bat. So I can move the things with the minus signs to the right side. I can add them over, factor out I bat, because it's a common term, and then divide the factored part. So I get I bat comes out to be delta V bat over R234 plus R1. And put that in. Delta V bat, we decided, was 15 volts in this problem. R234 we have calculated to be 5.31 ohms. R1 is known to be 11 ohms. Therefore, I bat let's see, comes out to be 0.92 amps. Alright, so I can put that in my table now. So in my equivalent circuit, the I bat in that circuit is the same as the I bat in my original circuit, because they are equivalent. Alright, so here's my original circuit. For the battery, I now know the current is 0.92 amps. The delta V bat was given, that was 15 volts. Okay, now we're going to continue starting with our equivalent circuit. We're now going to work back to the original circuit. Alright, we have to find everybody's current and voltage difference. Well, let's start with R1. So we just found that the current of R1 is equal to the current of the battery, because they're in a series. There's no junctions between R1 and the battery. So I'm going to put that in as 0.92 amps for R1. Delta V for R1, we're just going to use Ohm's law for that. So delta V magnitude 1 is just I1 R1, but I1 is I bat. So I'm going to let's see, calculate that. It comes out to be 10.1 volts. Alright, if I sub in my delta V and I put in R1. R1 is known to be 11 ohms. Alright, so now, knowing that voltage difference allows me to find the voltage difference across this equivalent resistor. I'm going to go back and use my loop rule now. So I know that the three voltage differences in my equivalent circuit all sum to 0. So now I'm going to use the known voltage changes for R1 and the battery. I'm going to solve for delta V234. Alright, so delta V234 in magnitude, I'm going to move that to the right hand side, add that to both sides, and what's left here is delta V bat minus absolute value of delta V1. That's from my loop rule. And so this is 15 volts minus 10.1 volts. That's the magnitude of that voltage change. So that gives me 4.9 volts. Alright, I'm going to go back to my table and put that in. So notice, let's see, I'm working from this equivalent circuit here. I just found that voltage difference, delta V 234. Well, but that circuit is equivalent to this intermediate one that I had. So this is also delta V 234. Okay? Well, that's helpful because that voltage difference is also the voltage difference of resistor 2. Because resistor 2, you know, the wires at the two ends of resistor 2 are the same as the wires at the two ends of this equivalent resistor. Alright? So, I can go to my original table now. I'm going to take what I just solved for, which was delta V 234. I got 4.9 volts in magnitude. That's an absolute value. I'm going to put that up here for resistor 2. 4.9 volts. I'll just make a note. We found that by the loop rule. I'm going to go ahead and put the signs here. So the absolute value was 4.9 volts, but because it's a resistor, that's a drop. Same for R1, that was a drop. The battery has a voltage rise. So these voltage differences are not absolute values. Some of these are plus and some of these are minus. Okay. What else can we now find? Well, if I look at Ohm's law, I could find the current of resistor 2. So I would just use I2 is delta V2, absolute value, over R2. And so that's easy. That comes out to be 0.65 amps. Okay, great. So the next thing I would do, I'm trying to do the easiest things first, I would say, okay, go back to this equivalent circuit here. This is my junction A that I was labeling earlier. And in this equivalent circuit, I know I bat, and now I know I2, because I just found it with Ohm's law. So now I can find the current through resistors 3 and 4, or through that equivalent resistor to 3 and 4. I'm going to use the junction rule. So, I'll just put that over here in my table to save some space. So, junction rule would say that this is at junction A. I bat has to equal I2 plus I34. The current going into that junction A was I bat, and the two currents coming out were these guys. So they have to add together to equal I bat. So therefore, I34, which is equal to I3, right, is I bat, which is 0.92 amps, minus I2. So that gives me 0.27 amps. 0.27 amps. This is also 0.27 amps. Again, the reason I can do that, looking at my equivalent circuits, this current through that equivalent resistor is the same as the currents through resistors 3 and 4, because those were making a series. The current going into that equivalent resistor, or coming out of that equivalent resistor, is the same as the currents that's going through resistors 3 and 4, because they're in a series. Right? Okay, so now we've found all of the currents, and now we just need to find the final voltage differences. So I'm going to use Ohm's law, because that's easy. So I'm going to say delta V3 magnitude is I34 times R3. I'm going to apply Ohm's law to resistor 3. And that'll give me the magnitude. I'm going to put a minus sign because it's, again, a drop in voltage in R3. And so I'm going to put 0.27 amps times R3, which was 6.2 ohms, and I get negative 1.7 volts for that. You can check the arithmetic yourself. I'm going to do delta V4 is minus I34 times R4. I didn't put the absolute value this time. That shows you why it's going to come out negative, right? It's a drop. And that one comes out to be negative 3.2 volts. Okay. We can do a little bit of checking here. If you compare resistors, so looking at my original circuit, R3 and R4 together, that combination, is in parallel with resistor 2, which means that the total voltage drop across 3 and 4 has to equal the total voltage drop across resistor 2. So that's a nice check. The summation of these two is 4.9, negative 4.9 volts, which matches. So that's a good thing. Okay, and then the last thing we can do is calculate everybody's power. That's just the product of current and voltage difference. So if I take 0.92 amps for the battery and 15 volts, the battery is supplying 13.8 watts of electric power to the circuit. Resistor 1, I take the current times the voltage difference there. I get negative 9.3 watts, so it's taking electric energy out of the circuit. That's what the minus sign means for a resistor. It's converting that electric energy into thermal energy. Resistor 2, I take 0.65 amps and 4.9 volts. That is negative 3.2 watts. Resistor 3, I take 0.27 times negative 1.7. That's negative 0.46 watts. And then finally resistor 4 is dissipating 0.86 watts of electric power. And so a nice way to check if these are correct is add all of the powers removed from the circuit by the resistors. 9.3 plus 3.2 plus 0.46 plus 0.86 in magnitude. These guys add up to negative 13.8 watts, which is good because that's the same as the power supplied to the circuit by the battery. So it's a good check. Power in equals power out in magnitude. Okay, so we have reached the goal. We've found everything that can be found about every resistor and the battery in this circuit, and we checked our work to make sure that the results made sense. And we did that by reducing our complex network of resistors step by step to some intermediate equivalent circuits as well as a final equivalent circuit that only has a single loop, and then finding that loop rule to find the battery current. And then from there we could have solved a number of different ways you could have found everything else. As long as you're using either a loop rule, junction rule, or Ohm's law, it all should lead to the same correct answer. All right.